In this video, we're going to look at some alternative expressions for acceleration, different ways of writing and involving the chain rule. Okay, so let's just have a look. Now, the first one is if the acceleration is given as a function of velocity, we can use a equals v times dv dx, and we'll be seeing examples of that used shortly, but let me just point out how we get this. All right, remember a was the rate of change of the velocity with respect to the time, and we could write that as using the chain rule dv dx times dx dt. Now dv dx, but dx dt is just the velocity. All right, now and let's just tidy it up a bit more. We can also write that as just dv dx. The order of multiplication there doesn't matter. Okay, that's handy because that's actually now going to help us with the second expression as well. Okay. Now, the acceleration could be written as we've seen, v dv dx. How can I get v is the question. Well, I could get it this way. I could do d dv of a half times v squared. Okay, now d dv of this would be 2 times a half times v. The 2 and a half will cancel out, and we're just left with v, which is what we have here. Okay, and then dv dx. Now, what's interesting here is this whole thing is looking a bit like the chain rule, in the sense that if I did d dx, the derivative with respect to x of a half v squared, well then what I will get is this will be the derivative with respect to v times the derivative of v with respect to x. And that's exactly what we've got up here. And so again, we end up with a, the acceleration. So there's two ways we can express the acceleration. And when we're handling problems where the acceleration is given as some function of velocity, we can use this, and we'll see shortly examples of that. And when the acceleration is given as a function of position, then we can use this object here, and we'll see an example of that. So we're going to start with the second case first. Let's say the acceleration here is given as a position, as a function, of position, 1 over 1 plus x, where x is greater than -1. Okay, to prevent it from being undefined. Because if we had -1 in here, then we'd have 1 minus 1 is 0, 1 over 0 is undefined, so the acceleration would not be defined. And that's not real physical phenomena. You can't have a function that's going to express acceleration and then is undefined at some value. Okay, now v is equal to 0 when x is equal to 0 and t is equal to 0. We want to find v. So we're given the acceleration as a function of the position, and we want to find the velocity. Okay, so a is 1 on 1 plus x, so we use a as d dx of a half v squared. Okay, so d dx, a half v squared, is, which is the acceleration, which is 1 on 1 plus x. Okay, now if we integrate both sides with respect to dx, okay, now what would have been nicer had I just written in there dx for the reasons I've explained throughout this video. We're integrating all that object with respect to x. Okay, well, on the left-hand side there, we just end up with a half v squared, the material in the parentheses. Okay, and on the right-hand side, we're left with the natural log of 1 plus x plus a constant of integration. Okay, very straightforward. You differentiate that, you'll get 1 over 1 plus x. Okay, we're told that v is 0 when x is 0. Okay, so let's put v is 0 in there on the left-hand side. Well, that disappears to 0. And then if we put x is 0 here, we're just left with a natural log of 1, which, as we know, that's going to be 0 as well. And so we're left with c equals 0. Okay, and so a half v squared is equal to the natural log of 1 plus x. Okay, multiplied by 2, so v squared is 2 natural log of 1 plus x, and then v is plus or minus the square root of 2 times the natural log of 1 plus x. Okay, two solutions. Let's just go down a bit. Let's have a look at the other case where the acceleration is given as a function of velocity. And remember, if the acceleration is given as a function of velocity, we're going to use a equals v times dv dx to do a similar thing we just did in the last problem. Okay, so here we go. So the acceleration is given by 18 minus v squared on 200. We want to find v as a function of position. All right, now a is 18 minus v squared on 200, so we use a equals v times dv dx as we've seen, and so where the a is, we're going to substitute v dv dx, and on the right hand side we'll have 18 minus v squared on 200. So dv dx will be, we need to divide through by v, so that'll be 18 on v minus v on 200, and they're not hard to anti-differentiate. We'll choose this with this a common denominator, so v times 200. We'll have 18 times 200 minus v squared to give us 3600 minus v squared on 200v. And by the way, maximum velocity occurs when dv dx is 0, or 18 on v minus v on 200 is equal to 0, so that implies that 18 on v is v on 200. And we get v squared is 18 times 200 is 3600, so that implies that v equals plus or minus 60 meters per second. Okay, the plus meaning one direction, the minus meaning a different direction. Okay, now dv dx is 3600 minus v squared over 200v, so that implies that dx dv is 200v on 3600 minus v squared. Okay, all we've done there is just taken the reciprocal of that. Now we have separated the differentials here. Dx is 200v on 3600 minus v squared dv. It is a technique, but anyway, we anti-differentiate both sides. What we're anti-differentiating really is dx dv integrated with respect to x. Okay, all right. Sorry, integrated with respect to v. Sorry, and then the same on the other side too. So 200v on 3600 minus v squared dv. Now, what we're going to do is take out a factor of 100, but we're going to make it negative. So that gives us minus 2v there, which is the exact derivative of v squared, of minus v squared. So it's minus 2v, and that's the reason that was done. And so when we anti-differentiate that, we get x is equal to minus 100 times the natural log 3600 minus v squared plus c. If you differentiate the natural log of 3600 minus v squared, you can have minus 2v on 3600 minus v squared, exactly what we have here. Then we have a constant. Okay, and what we do before we solve for that, we will subtract the constant from both sides. So x minus c is minus 100, natural log 3600 minus v squared. X minus c divided by minus 100 is the natural log of 3600 minus v squared. Exponentiate both sides. That'll help us get rid of the natural log. We'll remove it on the right. And so we're left with e to the x minus c on negative 100 is e to the natural log of that object there. The exponential and the log will disappear, and we're left with the exponent of this object is equal to 3600 minus v squared. Okay, what we can do is add v squared and subtract the exponent from both sides. Add v squared to both sides gives us 3600 minus the exponential of that object, and that implies that v squared is 3600 minus, just using the index laws now, we can separate this into two parts, the same base here. When they're added together, they give us this object here. Okay, and you can see where we're heading. We're going to be calling this some sort of constant because it is a constant value. There's no variable in there. It's just exponential of negative c on negative 100, which becomes v squared is 3600 minus e to the exponent of c on 100 times e to the power of negative x on 100, and that implies that v squared is 3600 minus, we're going to replace this with a constant capital A here. Makes more sense. Gives this object, then v is plus or minus that object there, where a is e to the c on 100. Okay, and that's the main thing to apply here. we weren't able to find a particular solution because we weren't given particular solution, we weren't given the boundary conditions, but the point of the video here is that when acceleration is given as a function of velocity, we can use a equals v dv dx, okay, which we just did on that last problem. And if a is given as a function of position, then we can use this object here, which is shown in this first example.